Hi, welcome back to es346 Basic Thermodynamics. This is module 5.2 on steady flow devices, and this is in sections 5.3 of the textbook and the first two parts of 5.4. Here are the three learning objectives for this module. At the end of the module, you'll be able to develop a steady flow energy balance. You'll be able to calculate property changes through nozzles and diffusers, and you'll be able to calculate power input or output requirements for compressors and turbines. So first I want to go ahead and develop the steady flow energy balance for an open system. So here I have a control volume, and it's open to mass, heat, and work. So I could have mass coming in, I could have heat coming in, I could have work coming in. And I also might have those three components leaving. So I could have mass leaving, heat leaving, and work leaving. And I want to go ahead and develop an energy balance for this that happens at steady flow, meaning it doesn't change with time. So I'll write my overall energy balance. It says the change in energy is equal to the energy that goes in minus the energy that goes out. Now the change in energy of a steady flow system is going to be zero. So the left-hand side of that is zero. And now I'm going to go ahead and look at all the terms that are going into my system. And so I have a mass flow rate, and what we saw in the previous module is we multiply the energy associated that by its enthalpy. And for completeness now, we'll go ahead and include the kinetic energy term and the potential energy term. So the mass flow rate, or the mass, times the enthalpy, kinetic energy term, and its potential energy term. And there might also be heat going in and work going in. So those three terms all go into the system. And then I'm going to go ahead and subtract, I'll put this on the next line, what's leaving. So I'm going to have a mass flow rate times the same three components, the enthalpy, the kinetic energy term, and the potential energy term. I also need to subtract Q going out and subtract the work that is leaving the system. So this is my general steady flow energy balance. Often, since it's equal to zero, I'll go ahead and move one side to the other side. So I have the mass flow rate, H plus 1/2 V squared plus GZ plus Q plus W. All of that going in is going to be equal to, well, clearly all of that going out. So I'll just rewrite it here again, M H plus V squared plus GZ plus Q plus W, all leaving. So this is the most general form of the energy balance, assuming that it's a steady flow. Now, since it's steady flow, I could go ahead and actually take a DDT of this, just look at it over a rate time. So I'm going to go ahead and write this in the rate form, which is going to look very similar. I'm now going to have a mass flow rate, M, times these terms here. So H 1/2 V squared plus GZ plus now Q dot and W dot. And those are going in and in, recognizing all those terms are going in my rate form of M dot plus Q out plus the work out. And those are all in rate. So there's the rate form of the steady flow. And we'll often talk about rates for steady flow systems since they don't change over time. There's not really a beginning and an end to them. All right. I want to go ahead and look at nozzles and diffusers. But first, let's go ahead and just talk about what nozzles and diffusers are. So first, here's a picture of a diffuser. You've probably seen this on a jet airplane, where as the plane flies, air enters the system here. And if you look at this, you realize that the cross-sectional area at the front of this is smaller than the cross-sectional area at the back. So what that means is that it's the opposite of a nozzle. If I kind of look at the cross-section of it, there's material coming in and there's material leaving. And so what happens is the material slows down in a diffuser. The diffuser is the very first part of a combustion jet engine. So here I'm showing the whole cross-section of it where we have the intake, and this is where the diffuser is. We'll end up looking at all these components in this class. In fact, today we'll even be looking at the compressor part. Eventually we'll talk about combustion, and then there's the exhaust, which is the reverse of the diffuser, which is the nozzle. So that's examples of what diffusers are. Nozzles you're probably familiar with. Here's just kind of a traditional nozzle like you might see almost on like a garden hose, where now it's going to be the opposite. I've got a large inlet cross-section and a small outlet cross-section, and so the velocity increases as I move through here. Another place you run into nozzles, which you may not know or be as familiar with, is in steam turbines, similar to what we're showing in the diagram over here, where the nozzle sprays steam onto the rotors. And so that's what's occurring right on here if this was a steam turbine. Right, you can see right here's a rotor, here's a rotor, here's a rotor. These are the moving blades in this diagram. And so the nozzle sprays it onto the rotor, causing the rotor to go ahead and spin. There's also a system of stators, which are the stationary blades, and you can see those in the diagram right there. So the material moves through this way, causing the rotors to go ahead and spin and generate power. Nozzles on the rotary device don't quite look like the garden hose one, so here I show a picture of it. Since this cross-sectional area of this is round, this right here is what the nozzles look like, and there's a whole bunch of nozzles that go all the way around that can go ahead and hit the rotors. So that's what nozzles and diffusers look like. Let's go and look at that overall energy balance that we wrote for steady flow systems and apply it for nozzles and diffusers. So here I'm showing a nozzle. I have material entering and I have material leaving. My most general form of the energy balance, but there's a lot of things in here I can go ahead and cancel out. First of all, let's just go ahead and go from left to right. I see my nozzle here isn't particularly big, and also it's oriented horizontal. So this GZ term and this GZ term are most likely the same. I don't have any large changes in height, so I can go ahead and cancel those two terms out. Now, another thing with nozzles is that they tend to be pretty small, so there's really not much heat transfer going on, and often we can go ahead and neglect the Q terms in there as well. And we don't plug them in, so we don't have to put any work into them, and they don't go ahead and generate any power, so we can go ahead and remove them. There's also no boundary work because this is a controlled volume. It's not changing with time. The volume is not changing with time. So what you realize, I've got a pretty simple energy balance left over here. mH plus 1/2 V squared is equal to mH plus 1/2 V squared. And since all the material that enters here has to leave there for a steady flow system, I can even go ahead and cancel out those mass flow rates and be just left with H plus 1/2 the velocity in equals H plus 1/2 of the velocity squared out. And so there is the steady flow energy balance applied for a nozzle. And the exact same thing for a diffuser, because nothing in here depends on whether it's speeding up or slowing down. All right, let's go ahead and do an example problem here. And so what I've got is a steam nozzle, and it's asking for what the outlet velocity is. And so here I'm giving some inlet conditions. The steam comes in at 1 megapascal and 300 degrees Celsius. And I'm told that the velocity of the inlet is pretty small, so it's about 0 meters per second. And then here's a pair of outlet conditions, 100 kilopascals and 275 degrees Celsius. So I'm going to go ahead and write down my energy balance. It says energy in is energy out, and I can write this in a rate form because this nozzle is just operating at time. The rate that energy is going in, we just saw what we derived before, is going to be H plus 1/2 V squared, and I'll call my inlet conditions 1, so this will be conditions 1. My outlet will be conditions 2. That will be equal to H2 plus 1/2 V2 squared. All right, and I'm trying to find out what V2 is, so I can go ahead and rearrange this equation for V2. And V2 is going to be equal to the square root of, I'm going to have H1 minus H2, and then I'm going to go ahead and need to multiply that by 2, and V1 is 0 in this problem over here, so actually all I need is underneath the square root is 2 in H1 minus H2. So I've got two intensive variables. I have 1 megapascal and 300 degrees Celsius. I'll see that that is superheated. If I look on the table, so they're table A6, you get those values, and in fact, these values over here are also superheated. So I can go ahead and pull those off just on a different pressure table. So if I go ahead and put those numbers in, here's my square root, my number value of 2, and I have 3051.6 minus 3024.5. And those units are kilojoules per kilogram. And I want all of this to be equal to V2. And V2 I want in meters per second. So here's something to be careful about. A joule is equal to a kilogram meters squared per second squared. And so this is where the meters per second come from. So that means I want the left-hand side in joules. So I need to multiply the left-hand side by 1,000 joules per kilojoule. All that's underneath the square root. Those kilojoules will cancel. So now I'm going to have my energy, but in terms of joules. And so now if I go ahead and calculate what V2 is, V2 is equal to 232.8 meters per second. This conversion here of getting it from kilojoules into joules such that my answer is in meters per second is a really important part, and a lot of people miss that. So be careful when you're combining enthalpy terms and kinetic energy terms. Okay, we're going to do what looks like almost the exact same problem, but now what we're going to be doing is we've got air moving through the nozzle, which means that my energy balance looks the exact same. The energy balance doesn't depend on the material. So you can write that from before. We knew that V2 is equal to the square root of 2 H1 minus H2. So this is conditions 1 and conditions 2. Now, the only thing different in this problem, since I'm dealing with air, is that I'm not going to look up values at these two intensive variables. What I know is that H is only a function of temperature for an ideal gas, and in fact, H is equal to the heat capacity times temperature. So I'm going to go ahead and put that into this energy balance. There's my square root, and it's going to be 2 Cp T1 minus T2. And let's go ahead and put some numbers in there now. 2, and heat capacity of air, 300 to 275, so I can go ahead and get an approximate value. It's about 1.04. Those are in kilojoules per kilogram. My temperature difference is going to end up being equal to, it changes 25 degrees Celsius. And again, the units on here are kilojoules per kilogram degrees Celsius for that value of Cp. So again, I need to do this conversion of 1,000 joules per kilojoule, again, to make sure that my velocity units come out as I expect in meters per second. And this is 224 meters per second. So a similar order of magnitude number. Another sanity check is to make sure you're not coming out with numbers that are like 2 meters per second or 200,000 meters per second. All right, the next pair of devices I want to talk about are turbines and compressors. And in fact, we've already kind of seen them in the previous diagram. I'm showing here a different picture of a pair of a turbine and compressor, and this is for a power generation unit. So here I have a shaft that is spinning, and this first section right over here is the compressor. So material comes in, for example, steam comes in, and each one of these stages compresses it slightly more. And that's why you see it gets smaller, because the specific volume is getting smaller as it becomes compressed. Then what happens is energy is added, usually through a system of burners in the middle section there, and then it's allowed to expand through the turbine, which is this outlet region right here, and you see it gets larger, because as it expands, almost by definition, it's going to get larger, and that's what generates the power. And so what we're doing is this section here is generating electricity, because it's being driven. This one right over here we have to drive to go ahead and put input power. And so in a power generation unit, the amount of power generated by the turbine is always going to be greater than the compressor. That's why it actually net generates electricity. So let's look at the steady state energy balance for a turbine or a compressor. So once again, at the very top here, I've shown is just the general steady state energy balance we derived at the beginning of the module here. And now I've got I'm showing a turbine here, where I've got material coming in, material coming out, and these tend to generate work. So it's a turbine. So if I look at what terms I can need to include in here, again, it's oriented horizontal. I can probably go ahead and cancel out my GZ terms. They probably aren't significant. And usually these are well insulated. So usually there's not going to be any Q in or Q out. So if I go ahead and look at what's left, let's look left for the turbine situation. For the turbine situation, it's going to be generating work. So you can have work out. So my energy balance to the left is going to be M H plus 1/2 V squared is equal to mh plus 1/2 v squared plus w out. And that will be a positive value. The turbine component generates electricity. If I look at the compressor option, what instead of having the work out, it's just going to have a work in term. So what I'm going to have on the left-hand side is now m plus 1/2 v squared plus w in is equal to m dot h plus 1/2 v squared. Now, another thing I'll mention, a lot of times even these velocity terms can be neglected, particularly with compressors. They tend to be pretty insignificant. So you'll have to look at the particular problem. And if it doesn't specify a velocity or doesn't ask you for a velocity, a lot of times you can go ahead and neglect those terms as well. And in fact, then you would have a real simple one. I'll just write it for the compressor. If you can neglect the kinetic energy term, what you end up having is m times h plus w in is equal to m times h. And that is going out, and these are coming in. All right, so let's go ahead and do an example here. So what we've got is a steam turbine, and we're asked to find what the power is produced. So we know that work is generated by the turbine, so we have a work out term, and that's what we're trying to find. So we'll go ahead and write our energy balance, which is the rate that energy goes in is the rate that energy goes out. And if I look at the arrows going in, I have a mass flow rate times h. Let's call this conditions 1, those conditions 2. So that'll be m times h1 equal to m times h2 plus w, which is the work produced. So we want to go ahead and calculate what this work is. So I'm going to go ahead and bring it to their side. So work is equal to m h2 minus h1. I'm sorry, no. Work is equal to h1 minus h2. There we go. And I'm told what the mass flow rate is. So it is 0.2 kilograms per second. And so then I need to go ahead and put in my enthalpy value. So I'm going to look up, this is a superheated vapor. In fact, this is actually also a superheated vapor. If I get those off of table A6. So if I put in those values, I have 3479.1 minus 2875.5. Those units are in kilojoules per kilogram, kilograms per second. That's going to give me kilojoules per second or kilowatts. So go ahead and do that arithmetic, and it's 120.72 kilowatts. So that's the power produced by this turbine. Let's go ahead and do one more example. And now what I have is a compressor. And this is an air compressor, so a different type of material. And we'll throw another little change into the problem. Here we're going to have heat leaving this compressor at a rate of 1.5 BTUs per second. And what we want to know is the power requirement. So compressors require work, so there's going to be work input. So as always, I think it's best just to start off with the energy balance. It says the rate that energy goes in is the rate that energy goes out. In here, what I've got is my mass flow rate times the enthalpy plus the work that I'm trying to calculate. And then what's leaving is the mass times the enthalpy plus that Q that is leaving. So it's called the inlet conditions 1, the outlet conditions 2. So that's 1, and that right there is equal to 2. So I can go ahead and rearrange this to solve for W is equal to M H2 minus H1 plus Q. I'm given the mass flow rate at 0.1 pound mass per second. I know Q. The enthalpy value, since I'm dealing with air, again, I don't have tables for air, but I know that the enthalpy is equal to Cp times temperature. So I can go ahead and put that in there. So this is going to be M Cp T2 minus T1 plus Q. Let's put our numbers in there. 0.1 pound mass per second. The heat capacity of air, 0.24. That is in BTUs per pound mass Rankine. And then my temperature difference is 120 minus 65. There's my T2 minus T1. And then what we need to do is go ahead and add in our Q plus 1.5 BTUs per second. And again, I'll go ahead and do my arithmetic to find out what my work input is. That's 2.82 BTUs per second, and let's go ahead and convert that into horsepower. That's usually what compressors are rated in. So if I do that unit conversion, it's about 3.99 horsepower. So about a 4 horsepower compressor.